Well, thank you all so much for coming here. I think what ALU is doing is wonderful. I was so happy that I was able to come out here, and I'm really glad that you're all here to meet, and I'm excited. So my first lecture, I've never done lecturing before. It's my first time doing it. So I've been doing robots my whole life. This is my first time doing lecturing. So if I say anything that doesn't make any sense or is weird or something, then please let me know. And also, don't worry too much. I'm okay, but I'm new at this. So on the first lecture, I just wanted to cover kind of some of the fundamentals, some of the basics. You all know what a robot is, I think, for the most part, but I wanted to say a few words about it first so we could kind of have a common understanding. Okay, so what is a robot? Well, Asmo is a robot. It sort of looks like a robot. I mean, I grew up with the Jetsons, Rosie the robot. So this is another robot. This is a Boston Dynamics robot, four-legged walking machine. It's really fascinating. It's covered in sensors. It's some of the most state-of-the-art robotics that exists in the world. Well, this doesn't look anything like the other two. This is a Google self-driving car. This is the early prototype, the Lexus. And this is certainly a robot as well. So it's covered in sensors. These are radar sensors, I think. That's a LiDAR. There's another LiDAR there. There's a LiDAR, maybe some cameras on the roof. Another LiDAR there. It's filled up with computers. It's got extremely powerful computers on the inside. This is another robot, much smaller than the Google self-driving car. You can still see that's probably some sensors there, maybe some lights. It can roll around. It must be some kind of antenna maybe. Does anybody have any idea what this robot's for? Yeah? So this is a package delivery robot. And one thing I like about this photo is, some robots are meant to operate just in factories, but a lot of robots are meant to operate with humans. And so we talk a lot about the mechanical engineering, the electrical engineering, software engineering, but there's also something called HRI, which is human-robot interaction. So these robots are meant to interact with people. You've got to understand how are people going to use it, and what is the robot going to do to be useful for the people. So in this instance, the human interface for the robot is this package hold, so that you can place packages inside of it. Well, these are robots. These are the NASA replica robots for the robots that are on Mars. So when NASA sends a robot to Mars, if there's some problem they need to troubleshoot, they want to have a robot at home they can play with. So they always make two. These are the replicas they keep on Earth so that they can troubleshoot problems on Mars by trying out the same problems here. And that big one, they landed that with a rocket crane on Mars. Some of you have probably heard the story, but it's just fascinating. That thing's about the size of a Mini Cooper. And they couldn't land it directly on Mars, so they had a crane with rockets. And they lowered it with a cable from the crane while the crane was shooting rockets down. It's just fascinating. And it was terrifying when it was landing. The NASA engineers didn't know whether it was going to make it. They didn't find out till 8 minutes later because of the time delay whether or not it even succeeded. Here's another robot. So probably looks like some kind of a farming robot. It's got big knobby tires. Let's see, that's probably a battery. You see these little sonar sensors here. They look like sonar. You can see some pulleys. So it looks like those probably go down and turn the wheels. You got something in the back as well. And it's got ground clearance. So farms are typically rows. And so you've got to design it to be able to, for the application. So it's got clearance for the rows. This is another farming robot. This is a much bigger farming robot. So it's got huge clearance so it can go over, maybe large bushes rather than just small plants. It has some kind of a sensing apparatus there. These look like big motors to drive these wheels. There must be gears or belts going down into there. That looks like maybe some kind of a linear motor to do the steering. A big heavy-duty machine. Well, okay, this is another robot. This is called the FarmBot, and this one doesn't have any wheels, and it doesn't go anywhere. It stays in one place. But it still has some motors somewhere over there probably, and there's probably some motors up here. And it has this mechanical frame, and it's made so that it can go in an XY area. So it's called a Cartesian robot, because this way and this way it can form a grid over a space. And it's meant to be a home kit for a robot. It's open source. These are some more robots. So these are very traditional manufacturing robots. A couple of robot arms, or a whole bunch of robot arms. ABB robot arms. One of the students here had an internship at ABB, I think, right? Yeah. These are big, heavy-duty industrial arms. Looks like they could move thousands of pounds. I'm not sure if some of them are actually lifting up the car in this picture. This was just kind of a fun, short video. I love watching videos like this, and I'll just put it on for a little bit. But there's so many different machines in the world that do manufacturing, and there's some great videos on YouTube of all these different machines going. And somebody had to design all these different things. There's a lot of factories tend to be very mechanical, so there's not as much software going on here. Get some advertisements. But when I look at this, I just think about all the different mechanisms that you can make. And certainly, some factories are very mechanized. Other factories, like the Apple iPhone factories, do rely heavily on software. So there's computer vision software that will look at cameras as pieces are moving by to make sure that everything is lined up properly. They have very high tolerance requirements. You're making pasta, that's a spring for an automobile. And if you're going to be learning robotics, then in a way, you're learning to move machines like this. So you're going to make a machine, what's it going to do? Well, it makes springs. These look like some glass bottles are going through. So it uses a flame. That's sort of a fun piece. You have a robot that's actually controlling fire. And the bottles are rolling off here. We've got soda cans. We'll share the slides. Pickles. That's sort of a good one. I like this one because it just shows this is a very application-specific machine. You've got pickles are kind of a funny shape, so you come up with these mechanical designs to move the pickles. You've got chocolate and other things. Let's see if we can get out of this. Yeah, that was the machines. Okay, so what makes a robot a robot? Well, it's going to have some kind of a perception system. That's what's happening around me. It's going to be able to think somehow. It's a computer. But the thinking, if you have perception, you can see the world, you can hear the world, maybe you can smell the world. But what does that mean? And then, of course, the robot has some ability to perform some action. So what can I do because of this thing that I've sensed? Sense, plan, act is kind of a simple way of describing these different capabilities. So all the robots that I showed before have perception. They have some ability to do thinking, and they have some ability to perform some action. Perception means a lot of different things. So you could have something called an IMU. That's an inertial measurement unit, which is a combination of an accelerometer, which tells you which way is gravity going, or which way am I being pulled. So if you're accelerating, the accelerometer can sense that. And then a gyro, the gyroscope. And that will tell you how quickly is something rotating. So you get these little chips now. They're in mobile phones, and they're just they're less than $1, and they can tell the robot which way is up. So a robot flips over. We have our inner ear that tells us what's going on. Mammals all have this, and it's very important. Robots have this too with an IMU. You have, of course, LiDAR. We've all heard about LiDAR. It's basically it sends out pulses of light, and there's a very accurate timing chip in there that when it sends out photons, they're going to bounce off of the world and come back. Now, maybe if they go really far, you shoot them into space, or they hit something very black, maybe they won't come back. But if you have a very powerful little laser and you're shooting out these pulses of light, then you will get some photons back. And if you can come up with a scheme for actually a high-tech little timing circuit, you can actually determine how long it took. It's not very long. The speed of light is really fast. But we're getting really good at making these very precise timing instruments. And LiDARs rely on this principle to send out thousands or millions of points of light a second to be able to take measurements of exactly how far away things are. You also use cameras. So mobile phones have very cheap cameras, and they make really cheap sensors. Unfortunately, it's a little hard to make sense of the data. We'll get more to that, but it takes sort of some difficult or complex compute to be able to make sense of cameras. Sonar is something that was popular in the 70s and 80s. It's a very simple sensor. Sends out a little click, and there's a little a diaphragm, sort of like a microphone. It senses that click back. Works like a LiDAR where it sends out a pulse, and the pulse comes back. You see how long it took. but it's not very accurate. So we don't use sonar as much anymore, although robots today still use sonar as kind of a last mile of defense. LiDAR, for example, can't see glass, and sonar can. So you want to have a redundant sensor setup. So GPS is, where am I in the world? And then a software technique called localization, which is when you combine your sensor data to figure out where you are in the world. GPS doesn't work indoors. It doesn't work in what's called urban canyons, which is when you have tall buildings like this. The GPS satellite signals don't get to where you are. So GPS isn't perfect, and you need other localization schemes, which we'll talk about, to be able to keep track of where the robot is. And this is important because if somebody asks you to do something, you have to know where you are. I mean, I suppose if you're just sitting at a desk, you could keep your eyes shut, and it really doesn't matter where you are. But if somebody asks you to go in the other building and grab something and come back, then you need to know where you are. So microphones. Microphones are what can I hear? So if you just need to talk to a robot, then the microphones are useful for that. There are other things. If you have a specific process in a factory, there might be a sound that indicates a problem is going wrong, and you need to use a microphone to sense that. There are other specialty sensors, temperature sensors, distance sensors, position, and a lot of other sensors in the world. So that's all kind of little basics of perception. This is kind of a fun robot. I just found this image on Google. What is this robot trying to do? It's trying to cut cookies or crush them maybe. So it's got lots of different kinds of perception here in order to figure out what's going on. So it looks like there's these kind of a couple of different eyes here. That sensor I can recognize is a little depth sensor, and it's got another camera over there, and I'm not sure what that is. Maybe it's a microphone or another camera. Well, it needs the camera to be able to figure out where are the Oreos. It has other perception as well. So in this arm, these look like really big, complicated joints, and one of the things that on a robot like this you're going to have is torque sensors. So when it's moving down and the knife hits an Oreo, it's going to feel now that it's hit something. So that's important. When you write the software to cut the Oreo, you've got to hit the Oreo and push a little harder, and then you'll feel it drop like that. That's a kind of perception, and you'll have a software routine that's reading these sensors, and it's saying, okay, I can feel the pressure now, and then I felt it cut. Okay, now I'm done. Don't keep going, or you'll cut through the table, or the robot will bend its hand, or something will go awry there. Here's another kind of a robot. This is in a mine shaft, and this robot is covered in sensors and has wheels, and it can generate a map kind of like this here. So it's got a LiDAR on it shooting out these beams of light in this mine shaft, and as it drives, it keeps track of where it's been. It remembers the location of all these laser points, and then it puts it all together into one map. If we look more closely at a similar mapping robot, you can see this thing's covered in sensors. So it's got a LiDAR here, a LiDAR there, a LiDAR there. That looks like sonar, probably another one over there. It's got antennas, so these little white things. There's probably 4 antennas on this thing, and it might use all 4 of them in unison as a kind of a precise thing. Or maybe they're all 4 different sensors, so 4 different antennas. Maybe one's GPS and one is Wi-Fi or something like that. It also has these handles on it. So again, these are affordances for a human to be able to interface with this thing. In this case, you just got to pick it up sometimes. And I know I've designed robots without handles, and you pick it up, it's awkward. So just having a big handle on it can be useful. This one also serves as a bumper. So if there's a rock in the way, it'll just kind of shove it out of the way rather than it maybe going onto the robot. So that was perception, but there's also thinking. So thinking means computers. The sensors collect all the data, but the raw sensor data needs to be processed by a computer. The computer runs code to turn bits of sensor data into understanding about the environment around the robot. So LiDAR is just the data from a LiDAR is just a collection of distances. But what do those distances mean? Once you take all that data, the computer then decides what to do. So it's going to control the motors, light up lights, or make sounds, start up other programs, or send data somewhere. So you take all this sensor data, you've got to process it, and that's what the computer is for. So computers can be large or small. This sounds like a simple point, but it's important. So this robot right here, this is very simple. It has an Arduino in the middle. Looks like a GPS chip there. That's some kind of a Wi-Fi, some kind of a Bluetooth. This is Sonar. Now, an Arduino is really cheap. They're $10, $20. But it can handle these simple sensors. The Sonar just says, okay, I've got a distance, I've got a distance. That's not a lot of data to work with. The Arduino's fine. But then you can have medium-sized computers, so something as powerful as a mobile phone. If you play with a cell phone these days, you can run a racing video game in 3D or driving really fast through a virtual city. The mobile phone processors are able to take all this 3D data and represent something. Well, that's useful for a robot too. So over here you've got a computer, an NVIDIA Jetson TX1. That's about it's the same kind of a processor you'll find in a high-end mobile phone. And that can take bigger sensors. So this is a stereo camera that takes 2 cameras and then corresponds all the points in the vision to figure out an actual 3D representation of the scene. It's very computationally intensive, but this medium computer can do that. This computer can't. And the reason why I say that this is all important is that that's a $500 computer and that's a $10 computer. So if you're making a robot and you say, well, you know, I want to be able to avoid 3D obstacles. The Sonar is not going to work. I need a stereo camera. Well, great. The stereo camera is $500 right here. That's a Z stereo camera. This also has a 2D LiDAR on it, a Kuyo LiDAR. That LiDAR is a $1,500 LiDAR, a $500 computer, or sorry, a $500 camera and a $500 computer on top of a remote control car chassis. So yes, this robot's more capable, but it's also much more expensive. The trick is figuring out how to make something affordable. If you're engineering a robot for some reason, somebody's going to be buying them, and maybe they don't care how much it costs, but a lot of the cases you're going to maybe be operating a business, or you're going to be working for an employer who's operating a business. They want to make a profit, so they want to meet the needs of the application without having something that's extremely expensive. One of the things that's always been true about robotics is that you can usually solve any problem if you have an infinite budget, but very few people have an infinite budget, except maybe the military and Google and Apple or something like that. But in the real world, you do have these constraints, and the skill of an engineer is making it happen with the minimum resources that is truly needed. And so that was tiny computers and medium computers. They're also very powerful computers. So if you look at these self-driving cars, they have a lot of sensors on them. The next slide, I'll look at that in detail. But all those sensors pull out a lot of data. So these cars have server racks on the inside, multiple very powerful computers with a lot of RAM and a lot of processing power. It costs thousands and thousands of dollars for these computers. So again, you can do self-driving cars, but you better have a real budget for it. And then there's cloud computing. So Google and Amazon, especially, both of these companies operate huge farms of computers that they rent out by the minute or by the hour, by the day. And they have very powerful computers that you can just rent for 10 minutes at a time. So let's say that you want to generate a map of an environment that's very computationally intensive, but your robot only ever needs to generate that map once. Well, you don't want to put an extremely expensive computer on the robot to do that. You just get the robot to have kind of a big hard drive, collects all the sensor data and saves it. And then you'll write a program where you rent one of these computers from Google or Amazon, upload the data to the computer. It's a very fast computer. It costs a few dollars an hour to operate, but you can run all that computation, and maybe you operate it for 2 hours. It costs you $4. You shut down that machine, you download the data, you're done. So cloud computing is very helpful for robotics, because robotics often needs huge amounts of data only sometimes. Cloud is really good for that. But you must have an internet connection to do it. So that's a major constraint. It means you can't do it all the time, but you can do it for some of your things. So again, this is the current Google self-driving car, or Waymo, and you can see it's covered in sensors. So that's a LiDAR, that's a LiDAR, that's a really big LiDAR, and it also has cameras in there. I don't remember, but I think there's cameras back there. It also, well, I don't see them, but I think it had some radar on it as well. So this is just a lot of sensor data. Each LiDAR produces millions of points per second. And a regular old computer or a Raspberry Pi or a mobile phone, it's not going to have enough power to do all this compute. You need really powerful computers. So really driving this point home, if you have more work to do, it means you need more computers. So if you're going to follow a line, you can use an Arduino. But if you're going to have something that's coordinating the motion of 4 legs at once, while also coordinating the motion of some crazy neck that's opening a door and walking through it, this thing has really powerful and very expensive computers on it. So that was all perception and thinking And then the next thing is acting or influencing the world. So if the robot can't influence the world, I don't think that counts as a robot. If it's all it's doing is perception, it could just save the sensor data into a box, but, well, that's a sensor, but it's not a robot. The robots move. They typically move with motors. So this is a little humanoid robot made with a bunch of individual servo motors. This is a Fanuc robot arm, and it has these huge industrial servo motors that are not the same kind of servos as these. They're also called servos. The word servo really means moving and moving, knowing how much you're moving. So you move 90 degrees, you have a sensor that knows how much it's moving. If you just have a motor that's spinning, that's not a servo. But if you also have a position sensor on the motor, and you have a little software control system or an electronic control system, so that when you tell that motor to move 90 degrees, it does to some precision, then that's a servo motor. And you typically need some kind of a servo motor for robots so that you can move a precise amount. You know, when my arm moves, I can move my arm a specific amount. I'm servoing my arm. So robots use motors, but they also use other methods. So this Caterpillar tractor, well, it has some motors to move it down there, but these are hydraulics. So they're not electric motors. Instead, you have a tube, and you put a lot of pressure, hydraulic fluid in there, and there's a little stopper, and that pressure moves that stopper, makes that arm expand and contract. It's a very powerful way of moving things. It can be difficult to precisely control the hydraulics with a computer, so hydraulically operated robots are tricky. On those walking robots that Boston Dynamics makes, they used to use hydraulics, but now they use electric motors. There are probably some cost issues with control, but electric motors are really easy to control. And then there are other methods. So some robots operate with rockets. So this is the Falcon 9 landing, and this is a robot. It has sensing, it has computing, it has the ability to act upon the world and beyond it, but it's a rocket-powered actuation. So most of the work is done by electromagnets. This is a little diagram of a brushless motor, and this is an actual photograph of a brushless motor. Skittles here, which I'll talk about in a minute, uses brushless motors just like that on the right to drive the thing. And generally, the way that works on a brushless motor is that you've got 3 wires coming off of it, and you have an electric circuit that can energize different coils at different times. And that creates electromagnetism in here. These are permanent magnets around the outside. These are electromagnetic coils on the inside. And as you energize the coils, they make an electromagnet that pulls on the permanent magnets. And if you keep cycling the coils, so you do A and B first, and then you do B and C first, and then you do A and C first, that can create a pattern of electromagnetism that causes the motor to always be pulling on the next magnets, or always pushing on the magnets behind. And that creates that rotary motion. So you have an electric circuit that's run by software, where you tell the software what position the motor is in, and you have a little calculation to figure out how you should set those coils. The electric circuit actually arranges to set the power in those coils, and that happens many times a second, maybe 1,000 times a second or 50,000 times a second. Probably not 50, but maybe 20,000 times a second. You'll be adjusting the current in those coils to keep the motor always moving by always adjusting those coils. And then this one over here, this is a hydraulic servo motor. So this is kind of when Boston Dynamics was using hydraulics in the walking robots. And some of the walking robots, the big Atlas, the 2-legged one, still uses hydraulics in its legs because they're so powerful. It would use an electromagnetic hydraulic valve that's kind of like this one. So again, there's electromagnets that cause this valve to rotate, and as the valve rotates, it changes the way that the hydraulic fluid flows through it. So you have a source of pressure. This regulates the pressure, and you can control it with a computer. So it's an electromagnetic valve to control the hydraulics. So even in these hydraulic robots, if you want to operate them electronically, you'll use something that's driven by electromagnets. I say that the robots can sense, they can plan, and they can act. So acting, one way of acting on the world is motion. But there's also other things. You can send a message to somebody. So you can use a wireless signal. You can just say, okay, I've completed a delivery robot like this might send the message out to the world. And then a computer somewhere else in the world says, okay, here's your next delivery. That would be a way of interacting with the world. Windows feature update, that's cool. This other picture here is some security robots. So they're hilarious robots from Mountain View, but they have cameras on them and they can sense the presence of people. So let's say there's some intruder, then they'd send a wireless signal out. And the wireless communications often looks something like this. So this is a little digital chip. There's a circuit here. This stuff is really interesting. I know we got, I think, 2 electrical engineers here. So I'm really happy to talk more about this stuff, and we'll talk more about electronics another day. This is the antenna for a wireless circuit. I love wireless. It's like really interesting. I'll briefly describe my understanding of wireless. I did a little startup with wireless communications, so I know a little bit about it. But that antenna is like, okay, so we're living surrounded by electromagnetic medium. It's like you're sitting in a pool. And if you move your arms around in the pool, then you get waves in the pool. And we're immersed, just like you would be immersed in water in a pool, the whole universe is some electromagnetic carrier medium, like water would carry waves. And so if you sort of splash around in the electromagnetic medium, then that will create vibrations in the medium that will travel a little ways and dissipate in the same way that you would have waves in the pool dissipate. And when you want to create a wireless signal in the world, what you do is you shove electrons into an antenna. You shove the electrons in, and then you pull the electrons out. And you shove the electrons in, and you pull the electrons out. And that's like if you had a balloon and you shoved air into it and you pulled it out, the balloon would be going like this. And the antenna is doing that electromagnetically. And so it just creates these vibrations in the air, and not in the air, but in the electromagnetic medium that we're surrounded by. And I just think it's fascinating that you can do this, that you can move electrons in and they influence this electromagnetic medium, and you do this very rapidly, and then you have another device over here, and those waves move into its antenna. And when they move into its antenna, they push electrons out of it, and then they pull electrons into it, and they push electrons out of it, and they pull electrons into it. And you have a little chip like that one there, and a circuit. And that circuit can take those movements of electrons and turn them into really clear digital signals that you can read. And then the chip has a design inside so that when it gets certain vibrations, it turns that into digital codes. And then you connect that to a computer, and what you end up getting is a system where you put digital codes in one side. It influences the electromagnetic medium. That causes waves to propagate through the universe some distance, and they dissipate. And then when they get somewhere else, they'll cause an influence on the antenna there. That creates electromagnetic vibrations, turns into digital codes, and then you know your delivery was complete. So that's my thing on wireless. So again, you can influence the world with wireless, but you can also send out lights and sounds. So you can have a display, like this robot's telling you lots of information on its display, and this one's making a cute face. So then there's software. So there's so much software keeping track of where the robot is. So this is a cool little diagram. This is something called Monte Carlo localization. But generally what's happening is that every red dot is an estimate for the position of the robot. Now, the robot never knows exactly where it is in the world with perfect precision. So it has some estimate for where it is. And the way that Monte Carlo localization works is you come up with about 1,000 estimates for where the robot is based on what the sensor data it's seeing. This is something you would typically use with two-dimensional LiDAR data. You come up with a whole bunch of estimates for where it is. There's an algorithm for how this works that's described in this book, which my friend Buzz donated to us as one of my coworkers. This is a fabulous book that describes these algorithms in detail, so we'll talk more about that. But Monte Carlo localization is described mathematically in here. We come up with a lot of estimates for where the position of the robot is, and then you do something like an average of them to figure out, well, I'm probably here. And the way Monte Carlo works is you always trim off the bad estimates every cycle. You estimate it maybe once a second. You estimate a new cycle of positions, and you just trim off the bad estimates and add a few new ones every time. It's an interesting algorithm, and I probably haven't explained it very well. But there's lots more software. So this is an example of software that's doing analysis on an image. This is a neural net called YOLO. And the way this neural net works, this is an image classifier. So it is classifying things in the image. So if you see this is a movie scene, somebody ran through this. Well, normally you're not having robots processing movies, but it makes for an interesting little diagram. But when a robot looks at the world, it needs to understand, what am I looking at? I mentioned that taking the data from cameras is difficult, but neural networks, machine learning, AI, artificial intelligence, this stuff is making it finally possible to understand images with computers much better than we ever did before. So here it's labeling each thing and also putting a bounding box around it. So it says that's a person, that's a wine, that's a glass, that's a tie. And if you told a robot, go find the guy with the tie and ask him a question, then this is the kind of software you would use. But you also can use this kind of software to say, okay, go out the door. You might actually put all these classifications into a map. So if you want to know where you are in the world, and you know that there's some doors in the building, those doors aren't going to move. So they're really useful features to throw into a map. There's really a lot of software in robots. When you look at a robot, it's a lot of complicated mechanical engineering. It's a lot of complicated electrical engineering. But I'll tell you, it's 10 times more software than any of that stuff. It's probably more than 10 times. It could be 100 times. But you think about the engineering of the Golden Gate Bridge or some building in Dubai, some great engineering project, and the software on a robot is totally invisible, but it's just as big of an engineering project as some of these huge things out there. What's really great is that a lot of robots use open source software, and so you get people that have built these grand things already, and you can just download it and use it. You just add a little bit to it, and that's a really important part of software. But this is an example of software that keeps track of how the robot moves. So, this is a little mathematical abstraction that says, okay, a robot has a joint that rotates this way, another one that rotates this way. They're all offset, and you can do a lot of math to figure out, if you know the angles of the joints, where is the actual end of the thing in 3D space. And that's important if you want to pick something up without knocking into boxes, which is what this is showing. So robots use sensors to collect data about the world. The computer uses software to process that data and figure out what is happening and decide how to act next. The robot can move itself or other things, speak, transmit messages, and more to influence the world. There's a lot of different pieces to robotics. There's many different disciplines with sub-disciplines. Some people just write software. Some people design the mechanical parts. Others design the sensors or the electrical systems. Somebody builds the robots and somebody else fixes them. You can learn all of this, but you'll probably just end up being good at just some part of it. You'll have to work together with other people to make the robots happen. You can try to do it all yourself, but you won't get very far. So if you look at a real job posting for a robotics engineer, this is some company in Europe, and they're looking for a senior navigation engineer. So this is a person whose job it is to just work out the software necessary for navigation. So that means that I don't know what they're navigating. Maybe it's a robot with wheels. But if it is a robot with wheels, they don't have anything to do with the software that drives the wheels. They only have to do with sort of the overall, well, I want to go that way or that way, and probably also where I am. So it's a little hard to read here, but development of methods for free and constrained navigation in continuously changing warehouses and industrial environments alongside humans, robots, AGVs, which means automated ground vehicles, and other vehicles. Coordination of multiple robots at runtime for efficient handling of traffic situations in shared spaces. So this, these are these specific things. You've got a bunch of robots. You've got to write the software that sorts out, okay, if you're in a warehouse and you've got 10 robots, maybe any one robot could do the thing that you need. Well, probably you want to take the robot that's not doing something else and that's closest to what you're doing. So you got to write a software routine that does this. But if your software routine is not very good, you could lose productivity in this factory or in this warehouse. You want your warehouse to be as efficient as possible. And now you end up all of a sudden, you want somebody with a PhD or a master's degree that can figure out the most efficient way to do this. Because if you don't do it the most efficient way, your competitors will. They'll be 10% more productive than you, they'll have 10% lower prices, and everybody will use them and not you, and your parent company will go out of business, you'll lose your job, and you'll have to find some other robotics job. So there are just many very specific positions. So if you're interested in software, you're interested in electrical engineering, that's fabulous. You can do multiple things. And in my job, I do a little bit of mechanical engineering, a little bit of electrical engineering, not much in my current job, and a lot of software. My job is almost all software. I'm almost all Python these days, but I've also done a lot of C++. So you'll move around. You don't have to stay in one sub-discipline. But I guess the good news is if you're really interested in something, then you can kind of stick out there. And if you don't like it, everything you've learned writing software and general reasoning about the world and how to have a meeting and not piss off your coworkers and these other things, this will all be useful. But don't expect to do the whole thing, except maybe at home. As a hobbyist, I designed the whole robot because if it doesn't work, it's okay. It doesn't have to be perfect. Okay, so I think I have some slides on, we're looking at sensors for a little bit. So I mentioned Sonar before. It's going to send out a ping of sound into the world. It's a little click. And that's going to send out sound waves like this. The sound waves are going to bounce off of an object, and you'll get reflections back. So there's some mathematical formula here that sort of says, okay, if I know the speed of sound, then you can calculate, what's the distance. And that's going to look something like this. So this is an oscilloscope plot. So that's, we have all these oscilloscopes around here. Right here is one of those. So that's a plot of an electrical signal over time. And if you send out a big click on one of your transmitters here, then some milliseconds later, you'll get a response back. This is a very big click. You get a very small response back, but you have a sensor that's going to amplify that and say, yes, that was a response. And then this represents time in this axis. So the time it takes to tell you how far away that thing is. And this is an example of a robot with a basic sonar unit on it. It's kind of like that. Again, then we have these LiDAR sensors. So you're going to have something where there's a little, let's see, let me orient myself on here. So there's an infrared transmitter laser. So that's right here. And that's going to be shooting out a beam. It's hitting a mirror. This mirror is rotating. So the actual sensor just points up inside of this little assembly. And if you're going to be an engineer, you might be an engineer that just designs these parts. So there's some complicated electronics in here, those high precision timing things to be able to sense the time it takes for the photons. There's a rotating part, so there's some mechanical engineering, driving a motor, which has software, electrical engineering, and mechanical engineering, just in the design of this little sensor. That's going to shoot the laser beam out, hit the rotating mirror. Laser beam goes out, and then a reflected echo, it's a little wider, is going to come back. It's going to bounce off the mirror again and hit this photodiode receiver. And so you have a transmitter and a receiver. The mirror is rotating, and you have a little bit of software that keeps track of where it was pointing. So you say, okay, that took this long, that took this long, that took this long, that took this long. And then if you know the speed of light, then you can determine the distance to all these things. And so when you see a LiDAR on a robot, it's some little assembly like this, and it's going to spin around, has a couple of mirrors so it can actually point it up and down as it's spinning. And that will, and sometimes they have 8, 16, or 32 individual lasers at once, so you get many measurements at once. And ultimately, that's going to produce a view like this. This is what LiDAR looks like when you're looking at a road. So that looks like maybe a big vehicle, like an RV camper. This is just like the big road itself. These are some trees. It's maybe a sidewalk, maybe a driveway over there. So this is kind of how these sensors are actually constructed. And you can see they're kind of expensive because, well, maybe you know that they're expensive and you can kind of see why. There's really a lot of precision electronics. And things are moving and vibrating. It's still got to be high precision. It gets to be a little difficult. So what do you do with all these sensors? And by the way, how am I doing? I've been talking for a long time and maybe I'm talking fast, but how is everybody doing? Yeah? Okay. I'll keep going. If you have any questions, please stop me. Yeah?
What's the difference between the term robot and
I think bot is just short for robot.
Isn't it bot for software bot and robot for mechanical bot?
Oh yes. Okay. So there is the term. You're playing a video game like League of Legends, and you find out that somebody's cheating because they're using a bot, and that's sort of a pseudo term. It's a real word that people use. It pretty much means robot, but it means a robot only in the software world. So yeah, sometimes bots do refer to just software routines. And the word robot is kind of a funny word where people might use it differently for different things. But when I'm talking about robots here, I'm talking about all these kinds that do exist in the physical world. Yeah. All right. So if you've got lots of different sensors on a robot, then you have this software process called sensor fusion. So fusion is bringing something together. Asian fusion food is delicious, I think. But you have this sensor fusion. So you have maybe you have an IMU, and that IMU is going to measure all these different Greek letters mean all the different things you could measure. So you have the XYZ acceleration and the rate of rotation, and maybe your absolute orientation in the world as referenced by the magnetic fields that you're sensing. So sometimes IMUs have 9 axes, rotation, acceleration, but also magnetic fields. You'll have a camera, and that camera is sensing some kind of data as well. You have a GPS, you have a 3D sensor, you have odometry from the wheels. Odometry is a term that means, how much have the wheels spun? So if all the wheels are spinning, some of them are slipping a little bit. Odometry is not going to give you a perfect reference for where the robot has really moved, but it's some very important information. And what you do for sensor fusion is a software process where you take all of this different sensor data, you feed that into something. Now this diagram came from a program called Robot Localization, and so it's saying all the sensor data goes into localization. What I'm telling you is that you have a process, some kind of a process generically called sensor fusion, where you take in the GPS data. Now the GPS is, it's accurate to maybe 5 meters in the world, depending on whether or not you have spotty coverage. The odometry is really good at telling you, okay, I think I moved 20 centimeters, and it's not going to be perfect, but it's more accurate than the GPS for short distances. The GPS is more accurate for long distances. I'm going to put this information together, software algorithms called sensor fusion. You'll see something called a Kalman filter, which is a kind of a special kind of a mathematical filter that says, if my GPS data is going like this, probably the robot can't actually jump 50 meters in half a second and then come back. So that was a glitch in the data, I'll ignore it. That's the way the Kalman filter works, is it takes a kind of a model of the real world into account, so that if the sensor data is a little noisy, you can eliminate the noise that's sort of obviously wrong. You fuse all that data together into something called a state estimate. So the state is like, what is the state of the robot? Where is it? And a 3D state estimate is like, where is the robot in the world? This is a problem, localization. Where is the robot in the world? It's very important. And the thing that makes this important is that it's not perfectly solved. So you'll have different sensors depending on your budget and your application, and they're all going to be sort of good at coming up with a 3D state estimation. You have to put in lots of different sensors together and do sensor fusion to really come up with a state estimate, and it's going to be dependent on what your sensors are and your application, so it's something that you need to be aware of generally. So now we have electronics. Electronics move electrons. Moving electrons create electromagnetic fields that move the motors and perturb the electromagnetic medium we use for wireless communication. Moving electrons activate the coils in Ethernet circuits, which I'll explain in the next slide. And electrons in a FET, which is a little electronic switch, turn the switch on and off or indicate data like 0 or a 1 inside of a processor. So electronics move electrons. Here's an example with an Ethernet chip. So this is sort of an abstract diagram of an Ethernet circuit. And if you'll see these wires here, these are the wires coming out of an Ethernet cable. And then this is going into the computer. And the way this shows this diagram is there's a little coil here, but the wires coming out of the cable are not actually directly connected to the computer. There's this little circuit here that's shown there, and it's this funny electromagnetic coil. The way this works is you'll have electrons coming in the cable, and you'll have this changing electromagnetic field in the cable that sort of shows how represents the communication coming from somewhere. That's going to move through here, and that creates a magnetic field in this little piece of iron that makes another electromagnetic field here. And this is a way of making it so that the computer is not electrically connected to all this stuff that's coming from the wall. When you have a really long cable, you can get weird voltages that come into it from the outside world, and this kind of isolates that. So I don't expect any of this to really make a lot of sense right now, except to say that this is the domain of electronics. So you're an electrical engineer, this is the kind of thing that you'll deal with. If you're a software engineer, you probably don't care much about this. Although if you end up with a problem on the Ethernet chip on your robot, you'll suddenly be really concerned about this stuff. But electronics is kind of just this funny field that if you're not doing it, I think a lot of it sounds like voodoo, but it's good to kind of see what some of the pieces are. So ultimately, you get a changing signal here. That creates a changing signal here. But if there's weird high voltages on this side, the high voltages will not come out the other side. It protects your computer. Again, I mentioned the brushless motor before. So this is a diagram of the electrical circuit for driving a brushless motor. So you have here some kind of a, I think we're just ever so slightly out of focus here. Oh, that's about the best we can get. So you'll have some kind of a microcontroller. This is a PIC here, but it's just like an Arduino. And then you'll have a special chip that's the actual driver for these FETs. So a FET, which is a field effect transistor, sometimes you'll hear MOSFET, metal oxide semiconductor field effect transistor. These are the terms for these electromagnetic switches. They're really important because if you want to switch on a motor, maybe you want 48 volts and 20 amps of current. So this is a whole lot of power. This is 2 kilowatts of power going through this thing. And you want to turn that on and off. But you want to turn it on and off with just this little computer chip that's just putting out these 3-volt signals. And so what you do is you run them through a driver circuit that turns those little 3-volt signals into a 12-volt signal. And the 12-volt signal goes into the FET. And when you have voltage on a FET, it turns it on. And so when you turn it on, current flows. And if you take off the voltage, it turns off. And so you have, in this case, for brushless motor, you have 6 FETs here. And what you do is there are 3 coils, or 3 sets of coils on an electromagnetic motor. Those coils are tied together here. So if you have a coil, it has 2 ends. If you have 3 coils, you should have 6 ends. They make it a little simpler in a brushless motor, and they take one side of each of those, tie them all together, and that way when you put current in on one side and pull it out the other, it'll flow through one in one direction, and then go backwards through the other one to come out. And so if you put 1 amp through a coil, you'll have sort of negative 1 amp flowing out the other end on the other coil. And if this is something you're interested in, then you can really, of course, get into it. But if you have 3 coils, you want 6 FETs. So you can either, you hook up this to the positive voltage, like, let's say you have 24 volts, you hook this up to ground, that's 0 volts, you hook these up in your electrical circuit. And then when you feed 24 volts down into here, so you could turn on this FET, you could turn on this FET, keep all the other ones off. And then what's going to happen is 24 volts will flow down here. In the middle, it's tied to your motor. So right here, right here, right here, it's tied to right there, and right there. So what happens is 24 volts shows up right here. So that's right there. And then on this side, it's connected to ground. So you have 24 volts here, and you have ground here. So current will flow through the motor. And any one of these little things is called a half H bridge. And this term comes from, normally for controlling a DC motor, you'll have what's called a full H bridge, so 2 half H bridges, but it would just be 4 to control a DC motor. That lets you put current that lets you control current in 2 directions on a regular brushed motor. A brushless motor has 3 sets of coils, so it uses 3 half H bridges. So this kind of a circuit, you'll use the microcontroller, you'll write software that switches all these different circuits on and off to create changing magnetic fields in the motor that creates motion in the motor. This is what the electronics would be good for. This is an example of a brushless motor controller that I designed. So this is my little Arduino compatible product I sold on Kickstarter in 2013. I'll tell a big story about that on Thursday. This right here is that right there. So it's called a gate driver. And that's the chip that turns the 3-volt signals from the microcontroller into 12 volts to turn on and off the FETs. Does a few other things as well. These are capacitors. So if you're switching voltage on and off with high current, then you're going to be drawing a lot of power from your power supply. And if you can pull that instead, the brief burst of current out of the capacitors, then you'll have a cleaner voltage supply, and these end up being very important on the motor controller. There's also a little thing right here. This is a switching power supply. So this chip needs 12 volts, but this motor that I wanted to design can support anywhere from 12 to 60 volts. And so you can feed 60 volts in here from a battery, and then this little switching circuit here has a little switching, that's switching chip there, a diode, capacitor, 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 inductor, and that's a simple switching mode power supply that converts the 60 volts or 24 volts anywhere along that range to a nice 12 volts. That nice 12 volts is fed into here, and this uses 12 volts as part of the way it operates. You'll get a data sheet on this chip when you are trying to build this circuit, and it'll tell you all these things that you need. And then these are the actual FET switches here. So you see there are 6 of them. Also have 6 diodes. So when you turn on a coil and then turn it off, it gets really mad at you because it really liked the current it had. And so when you turn it off, it says, no, I want my current, and it'll start shoving voltage back at you the other way. That's maybe a weird description, but the diodes will protect the chip from the reverse voltages that are generated when you switch off a coil. And then these are the 3 leads going out to a motor. You can see also the microcontroller has a USB interface here, and I've got some various plugs that are used for connecting to a position sensor on the motor. So generally, in conclusion, robotics is a broad field encompassing a wide range of skills. So maybe the brushless motor stuff was really exciting to you. Maybe the Ethernet stuff was totally boring, and you want to find other people that think this is exciting and work together with them. Robots in general are complicated. They tend to be built by teams rather than individuals. You can specialize in just the parts you like and collaborate with others to build the robot. Now you just need to figure out what to do. So this week I've worked with Zubair, and we're going to work all together and come up with some new features for our robot. That's this robot here. So this is Skittles, and I've been working on 3D printed robots at home for a little while, and when I got the opportunity to come out here, I decided to design kind of a simpler robot. I have some bigger, complicated robots at home. So this is meant to be a simple robot you can make in a small lab with a 3D printer like the one over there that we've got here. So all this is made on a $500 3D printer that I have at home. When I say all this, I mean the plastic parts. So this plastic here. I've got these gearboxes right here, have planetary gears in them. It's really exciting. There's a motor on the inside. There's an electronic position sensor there. That position sensor knows where the motor is, and that's important for telling the motor where to go. There's 2 motor controllers here. So these are those devices like the motor controller that I showed you. They have, you see 3 switches here. There's 3 on the bottom, 6 switches on them. And then they have the driver chip and the microcontroller. Brushless motor controllers are all pretty similar. That has these communication wires that are going to a Raspberry Pi. The Raspberry Pi runs Linux, and all the software that I've written for this is written in Python. I really like Python. It's a great language. This is a cool thing. This is a neural network coprocessor. This is made by Intel, or a company that Intel bought. This will run neural nets just like you'd run on a GPU on a computer. So you saw that object classifier that was picking out all the people in the movie scene. This runs that same object classifier. And I've already kind of arranged it so that we can run the classifier and we can get the position of people in the image out of it. So there's a camera. The camera's dangling off right now because I flipped the robot over and broke the camera mount. But I printed another camera mount so we can repair the robot, mount the camera properly, and we can run this image classifier and we can detect people using this robot. If you can detect people, you can do something like follow a person around or just turn and face the nearest person. It's got a nice lithium battery here. This is a 3-cell lithium battery. Lithium batteries operate around 3 to 4.2 volts, depending on whether they're fully depleted or fully charged. So we've got 4.2 volts times 3 is the voltage that generally this operates at. Right here is a little 5 volts converter. So just like on my other motor controller, I had a 12 volt converter. Some of the things on here need 5 volts. So, well, the Raspberry Pi needs 5 volts. So I take the 13 or so volts from the battery here and convert it into 5 volts. I use that to power the Raspberry Pi. This little device here is a communications device. So there's a protocol for communicating over an electrical wire called CAN. It stands for Controller Area Network. It was invented by Bosch in the 1980s for doing communications on an automobile. It works really well for also doing communications on a robot. And unlike some of the newer protocols that have been developed more recently, CAN is simpler, which is really nice because it works just fine. I'm only controlling 2 motors with it. We're not doing anything really fancy. It works really well. Everybody asks me about this feature, which is the hook. And basically, it behaves like a caster. So when the robot's driving around, this just drags behind like a ski. And it was cheaper than putting a wheel here. So this is just a chunk of plastic you can print on the printer. And I wanted to make this very low cost. So this is just a simple caster. And we've got these big, beautiful tires. These aren't exactly cheap. You could have gone cheaper, but boy, I do love the big tires. They're neat. So this robot is called Skittles. And I designed it in January and February for this class. It's yours now. So this is here for all of you to have. I've brought pretty much enough replacement parts to build another one. So you can either repair this if it breaks, or you could try to make it 4-wheel drive, which would be cool. You could put another couple of wheels on the back. You could just build a second one or something like that. We've also brought some other parts here so you can design other things. And I'll talk a little bit about some of the projects that we can do with this. So there are some possible projects I came up with that you all can work on this week. One thing that would be great would just be adding LEDs, speakers, or a GPS module to the robot. So I brought all these things. This is sort of more of a software style project. Another one, and Zubir mentioned that somebody thought this was simple, but program it to move a precise amount, turn 90 degrees, move 2 meters, etc. I want to say that does sound really simple. The funny thing is, it's a little tricky, because if you try to program it to move 2 meters, well, how accurate is it? Is it going to go perfectly in a straight line, or is it going to go a little bit off? And if you wanted it to move 10 meters, now that's kind of a long distance. You could tell it to try to move 10 meters, but it might only move 9.8 meters, or it might not go in a perfectly straight line. And the problems that you would find in trying to do these movements are going to underscore the importance of some of the other software things I mentioned. So if you do localization on a robot, which I mentioned localization before, then localization helps the robot figure out where it is in the world. If all you do is you remember where you drove, keep your eyes shut and you just walk around, then at some point you're not going to end up exactly where you started. And you need to use these other features, localization and sensor fusion, to actually get it to work. So if you try to get the robot to move exactly 2 meters or exactly 10 meters, or drive 2 meters, rotate 90 degrees, drive 2 meters, rotate 90 degrees, drive 2 meters, rotate 90 degrees, drive 2 meters again, well, you should end up exactly where you started, right? But you won't. As you rotate, the wheels will have a little bit of slip. You have changes in traction that you don't always expect. Maybe there's a slight wet spot, or there's a little bit of dirt on the ground. And what you'll find is that you drive and drive and drive and come back, and you'll be somewhere near where you started, but off by a little bit. And those errors can actually be really important. If you're driving around a factory and you're off by a meter, you might crash into something. If you're driving a forklift around that's a robot, it could crash into something, knock a whole bunch of shelves down, kill somebody, or cost $1 million worth of damage. And these are the reasons why you need the more advanced software concepts like localization. So another software project you could do is person following. I also worked a little bit on trail following and I didn't quite get it to work. So I have the software there, and if anybody, I think I know maybe what I did wrong, and if somebody has any ideas and they want to try to do trail following, we could try to run that software and get that fixed. For electrical projects, you could design an encoder. Oh, bless you. For electrical projects, you could design an encoder board from scratch. So I think this is actually something that we'll do on our electrical lecture, is I'll show the PCB design software and how it works. And we'll take a simple chip, we'll look at the data sheet, we'll actually lay out the board. Now I've already done that. These sensors here are the encoder boards, but we'll talk about how to actually design them. Another thing you could do is, if somebody's going to do the software project to drive LEDs with software, you also actually need to have the LEDs. So I've brought some LED strips that are pre-made, and the software people can use those pre-made strips to just work out all the software you need to drive the LEDs. But then the electrical engineers might actually want to design, LEDs that are custom fit for the robot. So maybe they have a special shape to them, or you have all the right colors that you need. Designing an LED light ring for the robot would be cool. That's a human-robot interaction kind of thing, typically. So if you're looking at the robot, and let's say you programmed it to do person following, and the person following software doesn't see any people, well, you're going to look at the robot and you say, okay, robot, come with me. And you start walking, and it just sits there. And you're like, well, is the software, did the software crash? Or is the software running, but it doesn't see me? So the lights can say, when I see a person, I'll light up green or blue. When I don't see a person, I'll light up red. Well, now, when you look at the robot and you say, come on, follow me, and it's red, you say, oh, it doesn't see me. And then that gives you a quick visual indicator of what's happening. That's human-robot interaction. It's very important. Designing an LED light ring or using the LEDs in software, those are some things you can do. Another cool one is design a distance sensor interface board. So you can get little individual sensors that behave like the LiDAR. They're just a couple of dollars. They send out a pulse of light, and they receive the distance back. Now, they're not spinning, they don't have mirrors, any of these other things. They just get a single point. But they kind of behave like a sonar, only much more accurately. And you can look at the data sheets for those chips online, design a simple interface board so that you could plug that chip into a Raspberry Pi and actually use software to read a position sensor. And two things you might do for that position sensor are, you could either put one here and one here, so just off on the robot, so that if either of the wheels is about to run into something, we'll probably just stop or back up and go somewhere else. The other thing that you could do, and we'll look at the mechanical projects in a minute, is in the mechanical project, we might want to make something for the robot that allows the head to tilt up and down. And the robot can also turn its wheels to rotate like this. So now you put the camera on that, and now it can look anywhere in the world. Now, if you have a camera and it can pan and tilt as a robot's looking, you might want to put the distance sensor there. Now, you can point the robot at something and accurately know how far away it is. So even though the robot doesn't have a big 3D LiDAR that can do all this processing, when you actually want to know how far away something is, it takes a little time, but you just turn and look at it, and then you can know how far away it is. So that would be an electrical project, design an interface board for a distance sensor. For mechanical projects, as I mentioned, you could design a tilting neck for the robot that lets the camera look up and down. You might also look up and down and turn, but this robot's two-wheel drive and it can just turn in place, so probably just use that. And then something that's very important and will let people get familiar with the 3D printer easily and also learn the mechanical design software, design electronics enclosures or cosmetic enclosures for the robot. So if you notice, my robot, our robot, beautifully uses a lot of tape and zip ties to hold it together. And Zubir has talked about sort of coming up with a sort of a simulated business case for this. So let's say we're all a robotics company and you've got a prototype and you actually want to now ship it to a customer. Well, you're going to have reliability problems if this thing's held on with tape and zip ties, and the customer is not going to be very happy with the situation either. So designing the enclosures can make the thing more robust so that it can fall and tumble down the stairs, a wire doesn't get snagged, these other things. So that's all I have. That's my lecture on what is a robot. Questions, please. Yeah, yeah. Third time's a charm. Okay, okay, okay. Okay, well, it stopped working the second time, so it's working again. So it can do some nice low speeds. You can see when it switches direction, the way that caster just kind of helps keep it stable. I'll drive it around on the floor if you all can see. That weird caster on the rear works surprisingly well. It works off-road, it works outdoors, over bumps, going backwards. Yeah, so I could have printed a wheel, but if you mounted a wheel here, you'd want to mount a bearing as well. And yeah, bearings are pretty cheap, and I've brought you all extra bearings. But I just wanted to try it, and I'm pretty happy with it. You'll notice that it was meant so that the radius of this matches the radius of the wheels, so it gets a little bit of visual symmetry in the design. The camera, right now there's some software that's not running, so that the code is sitting on the robot, and when we log into the robot, we can run the code. And I'm doing the YOLO object classifier with it can detect 20 different things, including chairs and couches and people and dogs and cats and a few other things. But this one's set to right now it's only set to notice people. So the software just ignores things that aren't people, and it finds I think the largest bounding box of a person and only returns that one, just the way the Python is filtering the results.
How does it decide if somebody is a person?
Ah, yes. So it uses a convolutional neural network. This is an area that is not my area of expertise. So I'm very interested in neural networks. This is a term, machine learning or AI, that people talk about. Well, you can download this. So if somebody has already done the thing that you need, then oftentimes you can go on GitHub and download it. And that's what I did for this. I didn't train this network. Like I said, this is not my area of expertise. So I can download it from GitHub and run it. And unfortunately, I'll only get what it can do already. So this one was already good at classifying 20 things. But then one of the things that people do at Google and these other places is they'll be the people that will do this stuff from scratch, do it for the first time, do the research on this, figure out how to do it. Machine learning is this, it's a field that's been around for 50 years, but has only been really blossoming as a field of study in the last 10 to 20 years. Specifically, in around 2012, we started to get really good convolutional neural networks, which are really good at doing image classification. So for the longest time, if a computer looks at this image, it just sees pixels. It sees numbers. So each pixel has a certain brightness for the red, the green, and the blue. They're just numbers. And you just look at a whole bunch of numbers and you can't tell what they are. We had these techniques for trying to understand images with software before, and it typically had to do with trying to match the way that lines look, and it was not very robust. So slight changes in lighting or orientation would completely ruin our ability to do that. So if you're doing image recognition in a factory, then you can control all the lighting. You can make sure it's all correct. And we were doing that before neural networks in factories, just using very specific lighting to be able to make sure that everything was always the same. But neural networks now are dramatically improving our ability to understand images with software. And not just images, but also audio, so doing speech recognition using neural networks. Google is using speech recognition or neural networks to generate speech. So now when you talk to your OK Google, the voice generated, it used to be generated by taking the word, breaking it up into little chunks, and then making sounds for each one of those chunks, putting them all together and spitting that out of your speaker. And it sounded pretty robotic. The new things that they're doing is they're using a neural network to generate the wave file directly to make the sounds, and it's much more human sounding. So machine learning is a fascinating field. It's basically a way of writing an algorithm that uses mathematics to learn something. So if you feed it all these pixels of dogs and all these pixels of cats, somebody's figured out how to make it so that some basic mathematical formulas operating on this data will actually learn, really learn, what a dog looks like and what a cat looks like. It's one of the most exciting, interesting, and powerful new fields of robotics. And anybody that's even remotely interested in software, I would definitely recommend checking out neural networks.